Okay, hi group. This lesson here has lots of historical information in the textbook, and I would really encourage you to read through this section in particular because it's interesting to note that some of this science goes back almost 250 years. So we might think of technology that we see today as being uh, 20th century, 21st century technology, but the ability to measure pressures of gases and individual components of gases has been known for quite some time. So it started out, we read in the 1770s with a Parisian jeweler who discovered that air contained some component which supported the combustion of diamonds and another component which did not. Later on, this was explored further by John Dalton. We've come across John Dalton a little bit before with law of constant composition. Dalton did work on analysis of gases in the atmosphere, and he found that the pressures of certain components of air varied considerably. Water seemed to vary quite a lot depending on the temperature, he discovered. Oxygen, nitrogen, and carbon dioxide each had a pressure which was very close to its percentage composition by mass. And in this case, for the kilopascal unit, they're very close because 100 kilopascals is about standard pressure. So the total pressure of all the gases is about 100, so the percentage composition was naturally just a fraction of that. In a unit of pressure, the millimeter of mercury unit, the percentages would still hold up, but the values would be quite a bit different. So Dalton's analysis led to a statement of a law of gas partial pressures, which was that in a mixture of non-reacting gases, the total pressure of all the gases was simply the sum of all the individual or partial pressures. And he was able to isolate the gases, we presume, in order to come up with this law. So the law has two parts to it, which we'll explain a little further. If we just look at the visuals at the top here, we can sort of see what this law is all about. Pressure is due to collisions of molecules or particles, and the pressure in a vessel, whether it's a cylinder, pressure tank, or just simply in the room, is simply due to all those molecules striking the walls. The type of particles is not important. Whether the molecules are combined or whether they're separate is also not important. So essentially, molecules act independently of other molecules. And this works well if we assume ideal gases, which don't interact with one another and probably interact very weakly even with particles of another compound. So the visual here shows that the combined gas pressure is simply the sum of the individual particles. Now, if you like to count particles, you'll find that there's 8 particles in here and 12 particles in here. So the number of particles is not the same in both of those, but you'll also notice the pressure of these is different. This is at 2 units of pressure and this is at 3. The combined pressure of those two is at 5. So provided the amount of the gases, the temperature of the gases, and the volume of the gas doesn't change when we combine them, then the pressures are additive. Here's another example on the right, which shows that whether the particles are of the same type or different type, it's the frequency of collisions with the walls that counts. Whether the particles are all of the green or a mixture of green and blue, if we still have 18 colliding particles, then we have pressure due to those 18 collisions, regardless of whether it's a mixture of gases. So the formal statement of Dalton's law of partial pressures is somewhat a formula, and it's also somewhat an idea. So we assume that gas molecules act independently, which means that their partial pressures when the gases are mixed is simply the sum of all the individual pressures. So the partial pressures combine to give the total pressure.
The left, a mixture of ammonium nitrate and zinc dust. On the right, water. A few drops initiate an explosive decomposition of the ammonium nitrate that generates a gaseous mixture of nitrogen, oxygen, and water vapor. The total pressure of the gas mixture is the sum of its components' partial pressures.
So in that very violent reaction, we can see gases definitely being produced. It wouldn't be obvious that there are three different gases being produced in that reaction. However, we could apply the law of partial pressures to that reaction and know that the three different partial pressures are going to contribute to the overall pressure of all the gas that's coming off of the solid. If we look at just summing up what we've seen so far, historical work from Dalton analyzing air, he did discover that 79% of air by mass is nitrogen and 21% of air by mass is oxygen. He noticed that water vapor pressure was variable and found that the pressure of dry air increased as water vapor was introduced to it. So his conclusion, which we know as the law of partial pressures, is stated there for you. So here's some visuals of how we can understand this law. If we look at understanding partial pressure as the pressure of the individual element or compound that's in the gas phase. If our container contains 4 molecules and they're all nitrogen, the total pressure is 4 units here, are not particularly important. If we have rather 4 particles combining 2 of one and 2 of another, our total pressure is still 4. If we look at whether this be 1 and 3 or 3 and 1, the pressure is still the sum of the individual pressures. So this is a fairly simple concept to understand. Now the explanation of this has to do with the fact that gas molecules act independently of each other. They move in straight lines, we assume, because their intermolecular forces are very weak, so there's nothing really causing them to interact. And simply put, pressure is due to collisions of molecules with container walls. So because of that, those two facts, as particles are moving around, they're going to be independently contributing their own pressure, based on how many particles are in the mixture from each of the component types. In your worksheet, you should also add some assigned work here. I'll just flash up quickly here, but we'll work on this in class. Okay, now when we look at Dalton's law, it can also be applied to the collection of a gas when the gas is bubbled through water. We did this in the determination of the molar mass of butane. Now what's really relevant here is that we appreciate the fact that part of the pressure inside the graduated cylinder was butane, but part of it was also water vapor. And when we do an experiment like that, we need to account for that partial pressure of water, which is dependent on the ambient temperature, the temperature within the collection vessel, or closely approximated would be the temperature of the room. So this partial pressure of water is going to increase as the temperature in the room increases. That would be reasonable. As we're getting closer to the boiling point, the molecules in the liquid state are going to be leaving into the gas phase to a greater and greater degree. So the vapor pressure will increase, not dramatically, even from slightly below room temperature to slightly above room temperature. The vapor pressure only goes up by a small number of kilopascals, but it's effectively almost doubling from 17 degrees Celsius to 30, even a little bit more than that. Okay, so we're not making a clear statement here about how exactly this relationship is on in an equation or as a formula, but we do know if we have a table, we can refer to this to account for the pressure of the water. So in your experiment, you should be looking at your pressure for water vapor, somewhere probably in this range right here. That needs to be deducted from the pressure in the room in order to come up with the pressure, which was simply due to C4H10 molecules inside our collection vessel. Okay, so when we refer to the pressure of water, we often call it vapor pressure. So let's have a look at what exactly vapor pressure is.
The vapor pressure of a liquid depends on the ability of the liquid's molecules to break intermolecular forces and escape into the vapor phase. A molecule can escape only when it has enough energy and is at the surface of the liquid.
Okay, so we understand that liquids can contribute partial pressure even if they're not boiling. So that's what that little clip was intended to show you. And in this sample problem would just be a real direct application of the law of partial pressures, where we're given the individual pressures of the component gases. Simply a matter of ensuring that they're both in the same unit and adding them together. So not much challenge involved in a question like that. Slightly more challenging question might be like number 1 in our student worksheet, 10.1a, where we have the temperature of water and we're given the atmospheric pressure. So the atmospheric pressure, we can assume, is going to be the total pressure. And we have to remember that the atmosphere is made up of all the gases that Dalton knew about, primarily nitrogen, oxygen, small amounts of carbon dioxide, and slightly more of water. So when we apply Dalton's law of partial pressures, we know that everything that is going to be contributing pressure needs to be accounted for. In this case, if it's done under controlled conditions, we can assume that the pressure of this gas mixture will be equal to the pressure of the atmosphere around it. And in our experiment, we will remember that we had to adjust the position of the graduated cylinder until the level of the liquid outside and in was equal. And that's when we knew that the pressure of the inside gas and the gases around in the atmosphere were the same. So the total pressure here would be equal to atmospheric pressure. And this would be the sum of the pressure of oxygen and the pressure of water vapor, because we have to remember anytime it's stated that it's collected by the downward displacement of water, or that method of displacement of water, we start out with a full vessel of water and then we bubble the gas in. So water vapor will be present. In this case, 24.0 degrees Celsius corresponds to a partial pressure of 2.98 kilopascals of water. So going back here, we're going to replace pressure of H2O with 2.98 kilopascal units. And the pressure of oxygen would be slightly less than atmospheric. Pressure of O2 would be simply the atmospheric pressure subtract the pressure of the water vapor. So we've got 100.34 subtracting 2.98, and the units for that would be in kilopascals. You can check your answers as you go through the questions in the student worksheet on this solutions page here, and you see that we end up with 97.36. Notice also that the answer is reported to 2 decimal places. So just a reminder that when we're dealing with significant digits with addition and subtraction, we report to the limiting value of decimal places, which would be 2 in both cases. So I would encourage you to go through this student worksheet as well as the assigned questions from the summary page here, which are some for practice and then some to just wrap up the section. So hope this lesson was useful for you to understand this concept of mixtures of gases, and we'll try this together tomorrow in class.